Right, guys, today we're turning to trigonometric functions. And first of all, before we can proceed, I would like to discuss briefly evaluating trig functions for any angle. Remember in school, when you deal with trig, you had a right angle triangle. Then we will talk about all those things like opposite over adjacent, blah, 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 blah. So now, in this situation, we want to define trig functions for angles which have really nothing to do with a triangle per se, but for any angle, even obtuse angles, more than 200, even more than 360 degrees, if we're talking degrees for now. So what we're going to do is let's have a situation like this. Let's say I've got a system of coordinates here. Right. This is the origin. Now, if maybe we have got something like this. What is important here? I think you must understand what is an angle, first of all. Now, if I put an arm here, starting from the origin here, then I can say that is arm of an angle. But first of all, what is an angle? Do you understand what is an angle? You understand? I suppose you roughly understand what an angle is, even if you cannot say what an angle is. Isn't it? If you don't understand what an angle is. Some people are saying, like yesterday, somebody said an angle is when two lines intersect, blah, blah, blah. I said, no, man. The angles have nothing to do with lines intersecting. Right. In short, guys, in maybe what you can call, I don't know what you want to call it. People sometimes talk of layman's language. I don't know who is layman. But angle is amount of turning. If I'm saying this is an angle, I'm just saying this arm from here, 0, the angle here, the measure of angle here, when this arm is on x-axis, is 0 degrees, if I'm using degrees. So if I turn this, obviously this point is fixed here. If I turn that much, this is an angle. That thing is small or bigger, the amount of turning, that's what I call an angle. Altogether. Maybe then in picture form, maybe you can then talk of lines crossing, maybe say this line turns from there to there. Okay, that's another thing. But otherwise, simple angle is the amount of turning. Altogether. So now, in a right angle trigonometric situation, right triangle situation, where something like this. But here I want to even be able to have an arm there of an angle and be able to talk about this angle and define the trig ratios without really a triangle. Altogether. Okay. So what am I going to highlight here? Firstly, I'm going to highlight that if we have got an arm of an arm like this, a ray like this one, I'll call this a ray like this one. I can pick a point there. This is the fact of life. If I pick a point there, that point has got coordinates x and the y. Do you agree? Now, if I get another point there, that point also has got the coordinate x1, y1. So any point along this ray, you have got those two coordinates, isn't it? Okay. What is interesting about this is that if I find the ratio y over x, I'm talking about this point, that ratio is exactly the same as y1 over x1. If you don't believe, take a graph paper, draw a line, test it, fill it altogether. But that is true. It happens like that. So the other interesting thing is, this point is at a certain distance from the origin altogether. And then this point is also at a certain distance from it. Let's say this point is at distance r1 from the origin, and this one is at a distance r from the origin. So what is also interesting that if we've got x over r, and that ratio is also going to be equal to x1 over r1. I can continue with that. So then, because this is interesting, actually, I think then these ratios, they are worth giving names. And then once we start giving names to these ratios, these are different ratios, of course, then we start getting what we call trigonometric ratios, sine, cosine, tangent, and so on. And I start with sine, because in my classes, my philosophy is that sine is the mother of all the trigonometric functions. Why do I say that? Because cosine is the sine of the complementary angle. Tan, I use cosine and sine. So everything starts from sine. Are we together? So that's fine. So what I'm going to do now? Let's start with this black ray here and say the ratio which we're going to call sine of theta, this angle here, let's give the name theta. The ratio we're going to call sine of theta is the ratio y over r. So it doesn't matter whether I use r or I use r1. If I use r1, then I have to use y1 because they are equal, isn't it? So what does that suggest now? This suggests that this is a function. What is in the domain of this function? This function sine picks angles and then assign them what? A ratio, which is a real number. Are we together? Do you see that? Yes or no? This theta is an angle. So it says sine of an angle, theta, is y over r, which is same thing is equal to y1 over r. In other words, in the domain of sine, I've got angles. In the range, I've got ratios which are associated with the angle. So in this case, as you can see, these two ratios, whatever point I pick, I get one ratio. So there's only a single assignment. Remember what I said? I said a function for a given input must give us a unique output altogether. So the unique output in this case will be a ratio. Never mind where you pick the point. Is that clear, guys? So then we talk of that as a function. Are we together? Okay. So now, when we come to cosine ratio of theta. Now, if you think about this point, for a while, let's think about this point. If we draw a perpendicular here, you will see actually that y is this length here. And r now will be this hypotenuse, which actually this agrees with what we saw there when there's a right angle. But the right angle will fail when we talk of a point here. The right angle cannot be there anymore. You understand what I'm saying? So we just talk of x and y, and we define our sine, we define our cosine. So our cosine now is going to be x, which according to the old language of right angle trigonometry, that will be adjacent to the angle over the hypotenuse. So we get this x over r, and which is same thing as x1 over r1. Are we together? So here we should understand that the right angle trigonometry fits into this situation, but this situation, the right angle trigonometry does not cover a broader situation. Are we together? So we're actually like increasing the scope of trigonometric ratios or trigonometric functions. Am I making sense? Okay. Right. So I hope we'll find that far. So now, as you can see, this angle theta we're talking about here, we are in the first quadrant. Are we together? Now, when you come to this point, to this line, red arm here, we are in the second quadrant. Now, this definition is going to remain that if I'm talking about this angle, do you see the arrow, ne? From 0 to the arm. If I'm talking about this angle, I can still define sine of, let's say now, I'll call it theta 2, just to indicate I'm in the second quadrant. Now together, that side is still going to be y over r. Let's say at the compass, you know what is a compass for drawing a circle? If I had a compass and fix the radius here, and they rotate the circle this way, would the r be different from here to there? No. Oh yes. No. But you see that if I reflect this black line onto the red one, theta is here and the theta is also there. I'm talking about this theta. Do you see that clearly? Then which means now when the angle I'm talking about here, the one which is represented by a red arc, that angle is actually 180 minus what? Theta. Do you agree? But y is the same, r is the same. What does it tell you? It tells you that sine of theta is equal to sine of 180 minus theta. I think you should know that from school, isn't it? Then, but if you don't know, then it might suggest that you are too young to be here. Are we together, guys? Okay. So in the second quadrant here, you can still do that. Now, but if you go, we define cosine. What's going to happen? If this point is reflected across there, x is going to be reflected somewhere there. Let me call this x1. And this side you've got x. This x here and that x1 there, they differ by what? In direction, is it? So this one will be negative and this one will be positive. I actually wanted you expecting you to say they differ by the sign in terms of negative or positive, isn't it? So now, which means the cosine of theta 2 will be x1 over r, but r will be the same, isn't it? So which means this x1 over r and this x over r, numerically they are going to be the same, but they are going to differ only by the sign, negative or positive, isn't it? But in this case, this one will be negative because the x coordinate here in the second quadrant is negative. Am I making sense? Am I making sense? Okay, so that's that. Again, you can find a relationship which is more or less similar to this one. I'll leave that one for you to sort out. All together. Okay, let me get this cleaned up here. Okay. Let me just take an advantage and extend this line. Extend this line in this direction. What happens? I'll end up in the third quadrant, isn't it? If I play around with my circle again, I think you can see that point will land somewhere there, isn't it? Again there, I've got x and y. But notice there, x is negative, y is negative, isn't it? You see that? And this angle here is actually theta. So this new angle here, I'll put it in green here. That angle there is actually 180 plus theta altogether. Then these two are negative. They will divide to give us positive, isn't it? But they are positive both. They will divide to give us positive. isn't it? So now, what I'm saying here is that sine of theta is equal to sine of 180 plus theta. Do you see that? And in this case, it's going to be given by y, which in this case is negative. No. This is here. I'm wrong here. Sorry. There I'm talking about something else. Just notice what's going to happen here. Let's just erase something here. Let's erase this. Oh. Okay. This sine, I made a mistake there. Say sine of 180 plus theta will be y over r. But now, if you compare this sine of 180, 180 plus theta, it's y over r, and this one of theta it will be y over r. But this y here is negative, isn't it? So what happens? These two numbers they differ by the sign. So which means at the end of the day, sine theta is equal to minus sine of 180 plus theta. I hope you understand that, isn't it? Okay. So you can work out that. Then a similar relationship you can get with what? With cosine. But when you come to what? To tan. Remember tan will be this ratio. We didn't mention it at the beginning, but this tan will be this ratio. So there and there it will be the same because the two coordinates are negative there, the two coordinates are positive there. The ratio of the two is positive. So tan of theta and tan of 180 plus theta will be the same. All together. Okay. Now that is in the third quadrant. So let's move on to the fourth quadrant and stop this discussion. Right? It's not picking my pen. Right. In this case, let's extend this one. Let's extend this one and come to there. Now, when you extend that one, you can see that this line, this one, and this one, one is a reflection of the other across the x-axis, isn't it? Then you expect this theta to be sitting somewhere there. Then, if we were to take that point there and the top of an angle this way, that angle would be 360 minus theta altogether. Then you can work again a ratio there. But if I rotate these coordinates from there to there, you see that the numbers are not going to change, but the signs are going to change, isn't it? So which means the ratio there and there and there, they are all numerically equal. They only differ by the sign, depending on the ratio you're dealing with and the sign of the coordinates altogether. So there's not really need to claim what is the sign of sign in the first quadrant. You need to remember that this is defined in terms of the coordinate. Just check the coordinate whether it's positive or negative, then you can determine the sign of the ratio immediately without putting a lot of things in memory, whatever. Altogether, guys. So then we can define that also for what? For a point there. You can define sine, cosine, and so forth. What is important is that these ratios, they don't depend on how far you are from the origin. It will be the same. Even if you chose to use maybe a radius here of 1, the ratios will stay the same. All together, guys. So now what I can say now at this point, I hope everybody is aware that now you can define cosine, sine, tan for any angle independent of a right angle triangle. Is that clear, guys? Is that clear? Okay. So I'm going to say maybe stop there for a while and say thank you for listening. The next thing is I'm going to introduce a new measure of angles. So far you've been seeing here, we need to talk about degrees. From now onwards, or from the next presentation onwards, we're going to learn a new unit for measuring angles. Thank you.